I'm gonna start the streamer and go to the notes somewhere.
That sounds terrible, don't do that. Oh, they lock you. Yeah, they make you play Starter Heroes for a little bit. That's different.
So for this class, I think we finished talking about comparison. Yes? Did we talk about the L flag, which is the exclusive or between the sign and the overflow? Okay, so we can finish that last topic in signed comparison, and then we'll move on to something more exciting. No, not something more exciting. All right, so I did add a module this morning, so nobody has a chance to read that just yet. It's about floating point numbers. It's very interesting because it's basically how do you use binary numbers to represent something that's not, they're not integers, right? So that's going to be interesting. We'll get to that part. And for now, we'll finish up comparison first. So comparison is binary number comparison. So this is the last topic that we were on. And we're almost done with it, not entirely, but pretty close to the end. So let's see, I'm pretty sure we talked about all of this stuff here, and also that we have two flags that we have to think about, and I think at least we have introduced the overflow flag, which is a 1 whenever the sign of the result of a subtraction doesn't make sense. Okay? But because it's binary, because we're dealing with binary numbers, including the sign bit itself, if it is a 0 and you know it is wrong, it's just as good as knowing what is right, because there's only one way for it to go wrong. Okay, so that's why the overflow flag is useful. Yep.
Is the audio working?
The audio should be working. Yep. So it is working right there. Yep.
Thanks for checking.
And of course, the best way to check is to use your phone to go to YouTube and try to listen to the stream with a 20-second lag and see if that was working. That would be like the ultimate test to see whether it's working or not. In fact, you can put on your noise canceling headphone and just rely on your headphone and your phone to listen to the lecture, except there will be a 20-second lag. Right, so you'll be looking at me, moving my mouth, but what you'll be hearing is something from 20 seconds ago. I'm pretty sure that's going to be a very interesting experience. Okay, so we got this part already worked out, and I think we are starting to get into the 4 possible ways to combine the sign flag, which is the most significant bit of a number, and the overflow flag, which is the indicator that the sign flag is wrong. Is that okay? So let's take a look at these 4, and not necessarily in this particular order. So I'm just going to point out to this one first. Okay, highlight it. Okay, so this one is basically saying the sign is a 0 and it is right. So if that is the case, what is the actual sign flag?
0.
0, very good. And we'll look up the other one, which is this one here. The sign flag is a 1 and it is correct. What is the sign flag? It's a 1. Okay, so the other 2 are corresponding to the cases where the sign flag is wrong. So the sign flag is a 0, but it's wrong. So what is it supposed to be? 1, exactly, which means less than, right? Because when the sign flag is a 1, it means the result of a subtraction is negative. And when the result of the subtraction is negative, the minuend is less than the subtrahend. Okay? And then the last one is when we have both the sign flag being a 1 and the overflow flag also being a 1. So in that case, the sign flag is a 1, but it is wrong, which means it is supposed to be a 0. So in this case, it is not less than. Yep.
Which one's the subtrahend and which one's the minuend?
Minuend is, okay, if you have x minus y, x is the minuend, and y is the subtrahend. But it's kind of useful, when I'm teaching the class so that we can differentiate which number are we talking about. All right. So as an exercise, I'm not going to collect this as a homework assignment. As an exercise, it is helpful for you guys to think about examples for all 4 possible cases. Okay? So you just come up with 4-bit numbers. I don't want you to spend too much time to write a lot of zeros at once. 4-bit is more than enough to find out, okay, if I subtract this 4-bit number from that 4-bit number, this is going to happen. And all 4 cases should be possible. Okay, so I want you guys to spend some time, just to try out all of these things, because as you try to find the examples and as you try to find out, how can I make the sign flag being a 0 and the overflow flag being a 1, you are going to understand, how all those things are supposed to work. Is that okay? All right, so it's a recommended exercise. I'm not going to collect the result. So for convenience, I'm going to define a new flag, which is L, which stands for less than, and it is the exclusive OR between the sign flag and the overflow flag. The way I do it here is just not using exclusive OR as a gate, and instead I'm using just conjunction, negation, and disjunction. It's the same thing that we did with R, the result after subtraction or the result after addition. It's just that whenever the sign flag is different from the overflow flag, L is going to be 1. Are we still doing okay, or are there any questions before I move on to the last section? Is that okay so far? Okay, so we might come back to this by the time we get to the comparison instruction when we implement this inside the processor. So food for thought is, now that we can see how subtraction of 2 signed binary numbers can overflow the result, what about addition? In other words, can the sign of a signed number after addition be incorrect? Okay, and the answer is yes. Can the addition of 2 signed binary numbers overflow the sum? And if so, how should we define the overflow flag for addition? So the question is telling you that it's going to be different from the way we define it for subtraction. Because when you add 2 numbers, okay, if you add a negative number to a negative number, the sum should be negative. But what if you get something that's non-negative? The sign doesn't make sense, right? If you add a non-negative number to a non-negative number, but you somehow end up with a negative number, the sign doesn't make sense. But the equation for that particular overflow after an addition is different from the overflow for subtraction. So I want you guys to think about it and see if you can derive that equation yourselves. Okay? I can go over the answer next class. Okay? But I do want you guys to have a weekend to kind of think about it, because once we have gone through subtraction, the cases for addition is not that different. Okay, so you have to think along about the same line, but it applies to addition and not subtraction. Is that okay? All right. So you have some informal, homework assignment. One is to figure out, specific examples for all 4 cases of all the combinations between sign and overflow to happen, and also try to define overflow for addition. So those are your informal homework assignments. I will go over the solutions on Tuesday. But by thinking about those things, I think it will help you understand the material a little bit better. All right. So I'm going to keep this slide here just in case there are any questions, to go back to here. But meanwhile, we're going to move on to a new topic. We're going to move on to floating point number representation. Which is interesting because when you think about all the values that we can represent up to here, up to now, they are integers. Okay, well, natural numbers for unsigned and integers for signed. Right? But they're all non-fractional numbers. So what is the easiest way for you to represent something that is fractional? So let's say you're dealing with SAE units, for wrenches and whatnot. Okay, for sizes of bolts, stuff like that. Does anyone know what is SAE? Okay, it stands for
The standard
Association of Engineers. So, but it's not metric, right? It is in inches, and not only is it in inches, it is in fractions of inches, where the denominator is always a power of 2. Okay. Hmm?
Yeah, it's you have 5/8 or something like that.
Yeah, 5/8, and then you have some really odd ones like 13, 30 seconds, and so on and so forth. So you have some really oddball ones. But it's actually much better than metric. If you haven't seen if you have a set of Allen wrenches, the hexagon, keys, the metric version only has like a few, because they go from 2 millimeters to 2.5 to 3 to 4 to 5. They go by millimeters. But the SAE version has a lot more in between. So you have really minor changes from one size to another size. Okay, so but the question is, what do you do when you have to represent wrench sizes that are fractional? And I want the easiest way out of this one, okay? Because if we can find the easy way out of something, we will use the easy way.
Maybe like a pair of values, so it's like 2 binary values.
Okay, so let's see how it would look like on a piece of paper. All right, so in terms of wrench sizes, let's say they're all less than an inch, because an inch is a pretty good size wrench. So we are limiting ourselves to maybe less than an inch. So we have 1/4 inch, we have 13, 30 seconds, and let's just say that the finest one you can find is 64ths. Okay, so we can find a wrench like some really super odd size like 47 64ths, which I don't think exists. Because that's a really, really odd size. Okay, but let's say this is all we're dealing with here. Okay, and your job is to figure out a way to represent these wrench sizes inside the database. Okay, so one way to do it, as somebody suggested, is to use 2 numbers, right? So we have basically 2 numbers. The first one is the numerator. The second one is the denominator. That works, but it makes it very difficult to compare these numbers. Because now you have a pair of numbers, the numerator, the denominator, numerator and denominator. Yes, it's very general, but to compare the sizes and to sort the sizes, it's not going to be easy, because now you have to look at the numbers. You have to figure out what is the largest, smallest common denominator, and all kinds of stuff like that. Okay, but we can do a little bit better. Okay, there's an easy way to do it. What about we change the unit? And we say we are not measuring in inches anymore. We're measuring everything in 64th of an inch. That is 1. Okay, so in that case, 1/4 of an inch would have an integer representation of what?
16.
16. Okay, about 13 to 30 seconds. 26. Yeah, and then 47 64th is just 47.
Times 2. Yeah. Okay.
Yeah. But now it's easy to compare, right? Because they're all measuring in the same unit, which is 64th of an inch. Okay, so this let me get away with continuing to use signed or unsigned integers without getting into fractions and all kinds of crazy stuff like that. Okay, but there's a problem with this approach. Okay, if you're an astronomer, you have a serious problem with this approach. Why do you think astronomers have a big problem with this type of approach, where we have when we have 64-bit integers, we still have problems? I mean, 64-bit gives you a lot of possible values. The range is pretty good.
I mean, more.
Okay.
Maybe you need even more specific.
Exactly, but in astronomy, we're measuring things. The things can be very large. Okay, what is the distance between galaxies? I mean, we're measuring in light years, okay? But light year itself may not be a good measuring unit, because at the same time we also need to measure something that's really close. So you might want to limit your measuring unit to a meter. So how many meters do we have in a billion light years? Which is probably the furthest object that we can actually observe using radio telescopes.
A number bigger than I can think of.
It's a pretty huge number, right? But at the same time, we also have to deal with very, very tiny numbers, okay? What in the universe is going to be very tiny?
Atoms, particles.
Okay. Well, vacuum is not actually vacuum, right?
Yeah,
There's always something, right? So when you want to measure the amount of mass per meter cubed in outer space, it's going to be a very small number. So we have a problem because we have to measure or be able to represent really big numbers and at the same time really small numbers. So we have an issue. This is not going to work because this one is fixing the scale. Okay, we need something that has a sliding scale and say that 1 unit is for this one unit is for this one. So the scale itself cannot be implied anymore. Like what we're doing here, we're basically saying the implied scale is 1/64 of an inch. Now we need the scale to be embedded into the representation itself so that we can say 1 is this quantity. Is that making any sense? Okay? So that's called floating point, okay? It's called floating point number representation. And from C and C++, how many people have encountered or at least have used doubles or floats? Okay, very good. So just about the entire class has some exposure to doubles and floats. Your professor talked about, when you break it down into individual bits, how the bits are used to represent the value.
I think he said don't think about it.
Yet.
Yeah.
Okay, because we're going to talk about it in this class. So your professor just didn't want to spoil the fun for me. Okay, so this is the whole thing, floating point number representation. I did not have enough time to finish the entire module, so I might have to catch up depending on how fast we go today in this lecture. Okay, and there are certain hyperlinks in this particular module because I want you to have access to the original article that I read. Okay, there's no need for me to hide and go like, oh, so Tech learned about this from Wikipedia. Yep, I learned it from Wikipedia. Why not? Okay, in some of your other classes, for instance, in political science or history, your professor may frown on you because you found something on Wikipedia. Okay, but when it comes to mathematics, computer science, technologies, that sort of thing, Wikipedia is not too bad. Okay, especially if you kind of follow up by looking up the reference links and whatnot. It's not bad. So when we right-click on this one and open this up, you can see that there's a big, huge. Okay, it's not huge, but it's kind of big on floating point representation. And the one that we are particularly concerned about is the binary 64-bit representation. So this is basically the description here. If I have to use one single equation or one single thing to express what is double, it's going to be this. Class dismissed, right? So let's take a look at this one. I have a slightly different way of presenting the same thing. But the idea is you have 3 chunks. Okay. The first chunk is just the sign, which is bit 63. The most significant bit is the sign bit. But this sign bit is really just the sign and nothing else. If the sign bit is 1, then the value being represented is negative. If the sign bit is a 0, the quantity it is representing is non-negative. It is as simple as that. There's no 2's complement, crazy stuff like that. Okay, it really is just, if the sign is 1, it's negative. If not, it is non-negative. The second part, which is in green, is from bit 52 to 62. So there's a total of 11 bits. That is the exponent. Okay, so when you add up, when you consider these 11 digits, okay, binary digits, as a unsigned number, in the documentation here, they call it E. But E itself is not the exponent of 2. It is offset by 1023. So you have to subtract 1023 from E to get to the actual exponent of 2. And that controls the magnitude. Okay? The mantissa is this part here. The 1 plus has to be there because it is implied. And then the rest is really the fractional part of a normalized mantissa in base 2. Okay? Are we doing okay so far or not? Not so good, huh? Okay, let's. Yep.
When you say it's 64-bit, you mean that it's represented by 64 zeros and or 1s, right?
You mean this one? 64-bit means that's the entire thing.
Yeah, so those are all zeros or 1s?
They're all zero. Each one is a 0 or 1. Okay. Yes. So each slot is a 0 or 1. The pink portion is the fractional part of the mantissa. The green portion is the offset exponent of 2. And then the last one, which is a light blue part, is the sign. Okay. So we'll take a look at one particular example. Okay, we'll take a look at one example and say, okay, tell me what this is representing. Okay. So I'm going to give you a particular example. Okay, so we are starting with, oops, switch to here. And I can fit more content because of the use of this thing here. Okay, so this is bit 63, this is bit 0, and this is going to be a pretty long strings of zeros and ones. But I'm going to use a value that is relatively easy to deal with. So let's say this is a 1 here. Okay, so we have a 1 over there, and then I have to figure out those 11 bits. So with 11 bits, what is the largest unsigned value you can represent using 11 bits?
2 to the 10th power, so that's like.
So it will be 2 to the power of 11 minus 1. Okay, what is 2 to the power of 11? 1024 is 2 to the power of 10. So you're off by 1, doubling it.
2096.
2047 is the largest unsigned number you can represent using 11 bits. Okay. So I'm gonna change this to. I just have to do some mental calculations really fast. Okay, so we'll have 1 1. Oops. Okay, 1 0 0 0 0. We have 11 bits. Okay, 1 2 3 4 5 6 7. There's 6 7 8 9 10 11. There we go. Okay. So let me just double check. 1 2 3 4 5 6 7 8 9 10 11. Okay, so these are the individual bits of the offset exponent. Okay. And for the rest, let's just make all of these zeros. All zeros for the fractional mantissa. Is that okay? So now the question is, if I look at this particular bit pattern as a double precision floating point number, what value is it representing? Okay, so that's our task. So the first thing we do is to take the sign bit out and go like, oh, the sign bit is a 1, so that means the whole number is negative. That's the easiest part. Then we take the exponent part and go, okay, this is the offset exponent, but let's figure out what is e by itself. So e by itself in this case is 2 to the power of 10, which is represented by this one here, plus 2 to the power of 1, which is represented by this one over here. So we have 1024 plus, oh, this is a 0. There we go. Plus 1, so the whole thing is 1025. But remember, the actual exponent of 2 is offset by 1023, so we have to remember to subtract 1023 from 1025 in this case to get to the actual exponent. So our actual exponent of 2 is 1025 minus 1023, which is 2 to the power of 2, which is a 4. Is that okay?
Can you do it one more time for me?
Okay, so these individual bits, when you look at those individual bits as one single unsigned number, the unsigned value is 2 to the power of 10 plus 2 to the power of 0. Because the one corresponds to bit 0 and the other one corresponds to bit 10 of that portion of the entire 64-bit number. Okay. So we have 1025 as a value represented by those individual bit patterns. But the entire exponent is offset by an amount of 1023. So you have to subtract 1023 from 1025 in this case to get to the actual exponent of 2, which in this case is 2. Okay? All right? What about this part here? This is the fractional part of the binary mantissa. In other words, the 1 point is implied. And then you just take everything here and say these are all the things to the right-hand side of the 1 point. It's a binary number. Well, I guess it doesn't even matter whether it's binary or not, right? 1 point blah, 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 1.0000 is always representing just 1. Because I got no fractional part. Is that okay? Then you take all of these components and you say -1 times 4 times 1 is 4. -4, sorry. So this entire bit pattern is actually representing the quantity of -4. Well, at least that's what I'm claiming. Is that okay, or are there any questions about the individual steps to come up with, oh, what is it representing? It's representing -4. Yes, go ahead.
So you subtracted 1023 from the original exponent, so is it always 1023 thing?
It's always 1023 because that's specified by the IEEE standard.
So if it's lower, so that original thing is lower than that, then it's just going to be a negative exponent?
Yeah, which is okay. You can. That's why you can represent very small quantities. Is when e itself is 0, then the actual exponent of 2 is -1023, which is a really, really small value. So that's why it can go really large, and it can also go very small at the same time. Yes?
So what happens when it overflows from this? Does it the exponent part go into the sign part, or?
No, you don't want it to. It cannot overflow. If the exponent of 2 is so big that it cannot be represented using this particular format, then that value cannot be represented as a double. Is that okay?
Yeah.
All right. Cool. Any other questions about this picture? Yes? It is different from float as a type, because in C and C++, float as a type is the single precision floating point number, which is 32 bit wide. So the width of the exponent and the mantissa are different, but the idea is the same. Yep.
Where'd you get the 1023?
The 1023 is a part of the specification.
Could you go back to the specification?
Yep. And there was one more hand. Can I? Yeah.
Yeah. I'm just curious, because I'm taking cisp310 at FLC. So we're doing it a little differently. How is the 1 and then the whole zeros and the 1? How is that a 10? How is that 10 to the 10?
Which one?
I guess the exponent, the 1, 0, 0, 0, and 1.
Because, okay, so you count the bit position, right? This is bit position 0.
Okay.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So bit position 10 represents how many 2 to the power of 10 that we have.
Okay.
Is that okay?
Yeah.
All right. Yeah, this stuff is supposed to be moved out of 440 also. Because we have to go for the CID template. So the CID template has different content in CISP 440. So this is the stuff that is supposed to be removed from CISP 440 and put into CISP 310.
Okay.
I'm not going to tell anyone what to do. I'm just saying what is, yeah.
What does it look like when it is like fractional from the negative exponents? Like, what does it look like when you do have a negative exponent?
When you have a negative exponent, then you multiply, then you have a 2 to the power of some negative power, so you can have a number that is less than 1.
Yeah.
Yeah.
But like, that'll be like 1/2 or something like that. How would that look there?
Well, let's figure that out next. Okay, so keep that in mind. Maybe something trickier. Let's try 5 30 seconds. Okay, so remember that. I'm going to write it down. So we'll try to represent 5 30 seconds. So we are given the value, and then we go back to figure out what it is, where the zeros and ones are supposed to go. Okay, so we'll do this, but we have to confirm this one first. So I claim that this particular bit pattern, 1 1, a bunch of zeros, and the 1, and then the rest are all zeros, as a 64-bit double precision floating point number, is supposed to represent the value of -4. And then what are you supposed to say? Prove it, right? Okay. Now, if I prove it by going through the same math again, it's not going to be useful because if I made a wrong assumption here, I'm going to use the same wrong assumption again. So the result will be consistent unless I make a stupid calculation mistake here. Okay, so what we will do now is we're going to use a trick, and we'll do a very simple C program to do it. Okay. So we'll go to the temp folder because I don't really need to save this particular program, and we'll just call this test.c. Okay, not very useful. Okay, so the program is just the main itself, and then I'll say double, is a D. And does anyone know how to use the concept of a union? Were you guys introduced to the C concept called a union? Which is not the same as CISP440, the set union. Nope, okay, I'm not going to use it. That's fine, not a problem. And I just need to do something here. Okay, so I'm going to do a little trick here. So I will start with that. What is that? What is %D? What does that mean? The address of D, which is a address of a double, right? Okay. Okay. This is a standard integer header file. It's really useful. If you have not used it before, you should start to use it because this gives you the ability to define types like this. Okay, so the types like this one is predefined here. So int64 uint64_t is defined in that particular header file. Now what it does is it will expand. It's a type def, but it's an architecture dependent type def to guarantee that uint64_t is a 64-bit unsigned integer. Now, is it called ultra super duper long, or just long, or just int? What do we care, right? If we get a 64-bit unsigned integer as a type, it's good enough. Okay? So this is really useful because if you don't do something like this and you just say, oh, it's int, and then you find out that int is only 32-bit long, 32-bit wide, and you say, oh, how about long int? Oh, it's still 32-bit wide. What about long int? Oh, now it's 64-bit. But guess what? That only works for that particular architecture. The next time you try to compile the same program using a slightly different architecture, it may not be the same anymore. So your values may go out of range, okay? And bad things can happen. But if you do it this way, it guarantees that we are dealing with a 64-bit unsigned integer. So your program becomes a lot more portable without you having to worry about, oh, should I use int or long int or short int over here? If you spell out how many bits it's supposed to have, it's guaranteed. Is that okay? So it's just a little bit of programming best practice kind of thing. So I'm going to do something like that. So what do we have now? What have I just introduced? What is that operator? It's a type casting operator. Okay, it's a typecast. In other words, I take D, which is double, I take the address of a double, it becomes the address of a double, and then I cast it into a pointer or an address of a 64-bit integer. Is that okay? Now typecasting is one of those things that you can do in C and C++, but not a whole lot of other languages, because it can potentially be very dangerous. It is you telling the compiler and say, don't complain, I know what I'm doing. Okay? So if you claim you know what you're doing, the compiler will just go, okay, hands free, go ahead and do whatever you want. Okay? If that turns out to be not what you really want to do, the compiler cannot check and warn you anymore. Okay? So now we take this whole thing. I'm going to put parentheses around the entire thing, and I put an asterisk after that, before that. What is that now? Now we have a 64-bit unsigned integer, don't we? Because I just dereferenced the address of a 64-bit integer. But it's not really a 64-bit integer, it's really a double, but I'm pretending that it is. Is that okay? So now, on the other side of the assignment statement, I can now give it the bit pattern for that thing that we just created earlier. Okay, I can read it off of my notebook here. Okay, so I'll group. Okay, I might as well show you guys how to do it. Okay, so the way to do this is to turn it into a hexadecimal number. Okay, we haven't really talked about hexadecimal number, but it's really, really useful, especially for something like this. So what we do is we group the bits by groups of 4. So here's a group of 4 right here, another group of 4, another group of 4, and then the rest are all zeros, but they all need to be expressed as groups of 4. Okay, so when you have individual groups of 4, then you look up a table. Okay, because 4 bits correspond to 1 hexadecimal digit, always. There's no division involved to convert between binary and hexadecimal, which is base 16. Okay. Now, because I've done this many, many times, I can just do it in my head. So 1100 is a C, 0000 is a 0, 0001 is a 1, and then followed by a whole bunch of zeros. How many zeros? In other words, how many zeros should I need to fill up 64 bits?
52 divided by 4. 13.
Very good. Okay. 13, right? 13. Okay. So I'm going to do a 13 append 0 escape. Oh, that didn't work. There we are. Yeah, there we go. Okay, so are there 16 zeros here? 16 move. Nope. 16 there. Yeah.
What does the 0x in front?
It means what follows is a hexadecimal number, base 16. Okay, so 4, 4, 4, 4. Okay, so we know that it is correct. Okay, there we go. All right, so we have a 64-bit bit pattern that is just kind of stuck into those 64 bits, and we want to interpret this number as a double. Okay, go ahead.
Do you have to put in X, or could you just put in the binary?
You cannot use binary in C and C++. C and C++ has no prefix for binary numbers. So the best you can do is either base 8, which is octal, or hexadecimal, which is base 16. Okay? So I'm going to leave the program just the way it is. But there's no printing, there's no C out. How do you know whether this thing is correct or not? I'll show you a trick. It's really helpful. Okay, no, I don't want to encrypt it. No. There we go. So GCC-G to include debug information, -O to specify the name of the output file. So I'll just call it test, and this is test.c. Now, technically speaking, we should all use warn all, just to have the compiler to check everything that is possible. Okay. And it compiles just fine, and it links in one single step. So now we have test as an executable. There we go. And we can just run it too, okay? Nothing happens because there are no input or output statements. So it doesn't do a single thing from our perspective. But if we do this, you can list the program, put a breakpoint on line 6, run the program. So now we are about to execute the return from main, but the program doesn't do anything. Well, it almost did not do a single thing, but it did one almost useless thing. It has one single assignment statement, doesn't it? So when I use print inside GDB, it will actually look at the type of the variable and print it according to the type. So it's not going to print me the actual internal representation of the zeros and ones. It will print the value represented by that particular variable. So here's the moment of truth, okay? It is -4. Are we doing okay so far with this? Sort of? Sort of. Okay. Well, sort of is good. It's better than no, I have no idea, right? Yep.
How do you use breakpoint?
How to use breakpoint?
Yeah.
You just do a B. You know, B is the command to set up a breakpoint, and then you give it a line number or a label. You can give it a function name, so it will put the breakpoint on at the entry point of a function that way. Yep. Yeah, this is GDB. You know, if you want to learn GDB, you know, one way to learn it is just help. Okay, because it does give you categories of commands, and then each one has its own, you know, list of commands and stuff like that. So it's really helpful to learn GDB. I know most of you used code blocks before. You know, code blocks is based on GCC, G++, and GDB, but the graphical user interface does not offer every single option available in GDB. So knowing GDB itself is always helpful. Yeah.
We're using your power server in our 400 class. Is that GDB?
Yeah, that's GDB itself. Yep. All right. Okay, so we got one problem solved. So now our next problem is to look at the value of 30 seconds, and we want to figure out how it is represented in zeros and ones. Okay. So what we need to do now is to say, I want something that looks like this. Okay. I need to know what is the sign of the value. Easy peasy. This one is not negative. Okay. I want my mantissa to look like this as a base 2 number, 1 point blah 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 blah. Okay, in base 2. Okay, and the actual value will have to be multiplied by 2 to the power of some kind of exponent. So we want to look at 5 divided by 32 and say, can we fit this value into that format? That is the question. Is that okay? All right. So what do you think we have to do in this case?
We have to do the division to see what it looks like, right?
Okay. So well, first thing first, we'll take up the easy one first.
Oh, yeah.
It's a non-negative number, so we have the sign bit being a 0. Oh, okay. So the sign bit is a 0, easy peasy. That's the easiest part of this entire thing. The second part is a little bit kind of, I don't know how to do this, because I need the mantissa to be 1 point something. Okay, but the value that we want to represent is 5 divided by 32. Yep.
Would you have to like shift it or something like that?
Exactly. We have to shift it. So we want to look at, one way to do this is to look at 5 32nd and say, how do we express this as a binary number? Okay, and then we'll shift it until it becomes 1 point something. Okay, that's one way to do it. There are other ways to do it too. So when you look at 5 over 32, okay, how would you represent it? How about this 5 times 1 divided by 32? Yeah? How do we represent 5 as a binary number? 0, 1, 0, 1 in base 2, right?
Yeah.
What about 32/32? A single 32nd.
Could you make it into the power of something first, or?
Okay, so let's do it step by step. That's a good idea. So 32 is 2 to the power 5, right? So this becomes 0, 1, 0, 1 in base 2 times 2 to the power of -5, right? I mean, you're just taking the denominator and negate the power. Okay. Can I claim this? Let's see. It's the 5. Okay, so it's 1, 2, 3, 4, 5 in base 2. Okay. What the? Does it work? Well, let's think about it, okay? So the digit right to the left-hand side of the point is telling me how many 2 to the power of zeros that we have, right? And we know everything to the left of that is 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. That's going to the left-hand side. What do you think happens when we go to the right-hand side? It goes lower, right? What is lower? What is 1 less than 0? Negative 1. So this tells me we have 0, 2 to the power of negative 1. We have no halves. This tells us we have no quarters, no eighths, no sixteenths. We have 1/32. Is that okay? Sort of cool? So now we can take this one and go like, oh, okay, so can we just use the usual base 10 trick and just say, we can just move this entire thing over here. Sure, why not? Okay, so it becomes 0.010. Okay, I have to look at, nope, I missed one. Yeah, so it's 0.00101. There we go. In base 2. We can always double check. Okay, so we can say we got 1/32 and this is a 16th, this is an 1/8. So we have 1/8 plus 1/32. What do we get? 5/32. Very good. Are we doing okay so far with this conversion? Yes? Okay. All right, so now that we know the value that we want to represent is 0.00101, how many times do I have to shift to the left-hand side until we have it represented as 1 point something? Well, let's see how many times we have to move the dot, right? Because that's basically what we are trying to figure out. And I'm trying to find a pen of different color. Yes, red pen. That works. Okay, so what we want to do, what we are trying to do, well, the red pen is not cooperating.
I got it ready.
Oh, okay, thank you. Just remember to take it back.
I will.
Okay, so we want to figure out, how many times do we have to shift to get the dot over here? That's what we're trying to figure out. So if we shift once, it's here, twice, here, 3 times. Okay, so we have to move the dot, the decimal point or binary point, 3 times to the right-hand side until it's at the right place. Okay, so that means this is 1.01, right? The default power exponent of 2 was 0, but now I need to adjust for this shifting. Every time I shift the binary point to the right-hand side, I have to remember to adjust something in the exponent so that they still represent the same value. So we know this has to do with 3, but is it positive 3 or negative 3? It should be negative 3, because every time you move the binary point to the right-hand side, you are doubling the value represented by the mantissa alone. But we don't want to double the actual value that is represented. We want to keep the value the same. So when you change the mantissa, you have to adjust the exponent to take care of that shifting. So we have a negative 3 up here. Thank you. Is that okay? Does everybody understand why we have a 2 to the power of negative 3 here?
You jump 3 times or 2 times?
What happens when you, in base 10, okay? In base 10, what is the change from 0.01 to 0.001? This is in base 10. They're all 10 times, right? Okay. So if I make a number that used to be 0.001 and turn it into 0.01, okay, I have just multiplied the value by 10. But I don't want to do it that way. So what do? I say, oh, that's not the whole story. Now we need to multiply this number by 10 to the power of negative 1. I just did the same thing in base 2.
Yeah, just base 2, you change the base. Okay.
Yep. Okay, because we don't want to change the value that is represented. We just want to change how it is represented. Is that okay so far? So good? Okay. All right. So now that we know this is the number, we have a sign of 0, and then we have 0, 1, to start the mantissa. The rest are all zeros, okay? So they're pretty easy to deal with. And we have this one piece here. The actual exponent of 2, we want it to be -3. But we know that when we represent the exponent, it is offset by 1023, okay? So we know that e minus 1023 is 3. So now the question is, what is e? You guys can figure this out. Oh, -3, sorry. There we go. It's a -3 here, okay? 1020, okay, very good. So e is 1020. Now we have to turn this into a binary number. Ah, it is so easy. It is really easy, okay? So let me tell you why it is so easy. I can tell you what it is. It's all ones except for the least significant 2 digits. Those are all zeros. And you go like, how can you possibly do the binary conversion this quick? It's easy. Well, practice is one thing, but you know the trick is the other. 1023 is a whole bunch of ones.
Yeah.
So 1023 is basically 9 ones. Sorry, it's 9, 10. 9 ones. Yeah, 9 ones.
7 1s 2 0s.
Yep.
I was going backwards from 1024 because it's 2 to the 10. It's just a 1.
Yep.
And then go backwards.
You can do it that way too. So we will start with a 1 because the 0. We'll start with a 0 because that represents that we have none of 1024. Okay. So here is the 1. So we have all ones here. So we have, let's see, we should have 9 ones. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oops, I counted wrong.
You mean 7 1s?
We should have 8 ones and 3 zeros. 1 leading and then 2 trailing. Because the whole thing has 11 digits. E has 11 binary digits. We know the most significant bit is a 0 because we don't have any 1024s. Right? And then the rest are supposed to be ones if we just want 1023, but we don't want 1023, we want 1020. So we have to subtract 3 from 1023. But 3 is easy because 3 is just 1 plus 2, which accounts for the least significant 1, 1. So we have to take out the least significant 1, 1, and we are left with 0, 1, 1, 1, 1, 1, 1, 1, 1, and then 0, 0. Yep.
You have an extra 1 there?
I don't think we have 1 extra 1. There are 8 ones, right? 8 ones would be right. But I don't trust myself. Let's double check. So if I don't trust myself, we can check here. So in GDB, now GDB is really cool because even though C and C++ does not let you enter numbers in binary, GDB does. And if I remember correctly, it has a it's 0t instead of 0x. 0t is the prefix for a binary number. So let me just test it for now, okay? 1010 is supposed to be 10. Oh, it just gives me 1010. Okay. Of course, you can always help. Say help. Okay, print the value of expression exp. Okay, you can print a whole bunch of other things. I just need to know the format. FMT. So we want to look at the X command. So see the last part here? exp may be preceded with /FMT, where FMT is a format letter, but no count or size letter. See X command here. So we can print as a decimal, which is a /D. Nope. I know we can do binary. I just cannot remember the prefix to do binary. There we go. /B is the prefix.
That makes sense.
Yeah, makes sense. So what is P? Cannot remember. Okay, so 0B is binary. So now we can do what we were talking about, print /d 0b, and then we have one leading 0, 8 ones, 1, 2, 3, 4, 5, 6, 7, 8, and then 2 trailing zeros. Right?
Shouldn't it be 7 ones? Because you
So let's
have
see.
it in- Well, actually, it's 11. Sorry.
Okay. So we got it. Okay. So getting back to the notes here, so we know this is the correct pattern for E, and we have a sign of 0, and then we have 0, 1, and then a whole bunch of zeros for the fractional part of the mantissa. So when you string the whole thing together, then it becomes 0 for the sign, 0, 1, 1, 1, 1, 1, 1, 1, 1, 0, 0 for the exponent, 0, 1, followed by all zeros for the mantissa, or the fractional part of the mantissa. So now we convert this into a hexadecimal number, and then we use the same trick but this time in GDB, and see whether we get 30 seconds back. Okay, so we group these things into groups of 4. So we got one group of 4 here, that's 3. We have another group of 4 here, 1, 2, 3, 4. That's an F. We have another group of 4 here, that's a C. And then we have another group of 4 here that is non-zero, that turns out to be 4, and then a whole bunch of zeros after that. Is that okay? Does everybody understand the process, the steps? You group groups of 4, and then for each group of 4 bits, you look up the hexadecimal digit, and then you just string the whole thing together. All right? So the whole thing becomes 3FC4, and then followed by 12 zeros. Okay? So now we go back to the C program. Okay, I can still see mine, on my paper. So the question now is, how do we retest this program? I don't want to get out of GDB, change the program, recompile, and then go back into GDB, set up the breakpoint again, blah, 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 blah. I can do everything inside GDB because I can now say set. So when you use the set command, you can set certain internal variables, but you can also use it to change variables used in the program itself. So I can change D using the set command. So I can say set, and then do the same trick, okay? D reference, and then do the casting 64_T, and we're casting D into a 60 I'm casting the address of D into the address of a 64-bit integer, dereference it, and then say, we are going to set that to the following. We set 3FC4 and then 12 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There we go. Okay, so now we say print D again. Now when you say print D, it automatically uses whatever type that comes with D, which is a double. Okay, so now we should see whatever the decimal representation is for 5 divided by 32. We know it's going to be a little bit more than 0.125 because 0.125 is an eighth, which is 4 divided by 32. So it should be 0.1 something something, right? Woohoo! And then you guys might think, but how do we know this is actually 30 seconds, right? Fine, we'll do it this way then. Now you have to double cast 5 first because otherwise 5 is an integer and 5 divided by 32 is just 0 because it's an integer division. But if you cast 5 to a double first, then it will also automatically cast 32 into a double, so it becomes a floating point division.
Which should be 0.
Yep. But if you don't cast it, it will give you back 0.15625. Little tricks that you learn because your program doesn't work. They go like, why is it not working? 5 divided by 32 is supposed to be 0.15 something. Oh, if you don't cast it, it doesn't know that you're dealing with a floating point representation of 5 and not just 5. Now the other way to do this is to make this 5 5.0 because that notation will trigger GDB to automatically say, oh, this is not integer 5, this is floating point 5. So that works too. So are we doing okay so far with the notation and how a value is represented as a double precision floating point number? That is a mouthful. Yes, no, kind of. The general idea?
Well, it was cool.
Okay. So now the biggest question is, when you have cin to read something into a double, are you typing all of these zeros and ones and going through all this conversion in your head when you enter a non-integer number into your cin?
No, we use base 10.
You use base 10, very good. Okay, so the question now is, how do we convert the number that you type in, which is a base 10 number, which can be in scientific notation, okay, into a double? How did that happen? Okay, now I don't want the easy answer. The easy answer is, oh, cin greater than. Yeah, well, that's just the syntax, right? So underneath that syntax, what is really happening to the digits that you type that will convert it into the internal representation using 64 binary digits?
I think how we did that.
Exactly.
Yeah.
So it's going through about the same process, but in general, it is actually a little bit more complex than the values that we have chosen to use. So let me switch back to the notes here. Okay. So the first part, which is in section 2, is really just saying how the number is broken down into various parts and so on. So it's for the most part, it's just a notation issue. So that part we have talked about already. Section 3 talks about what kind of range are we talking about, and I have some typesetting mistake here. This is 2 to the power 52, not 2 to the power 5 times 2. So I suppose I should change. I should fix that first. Yep. Okay. So. This is 9.6, and I'm looking for 2 to the power of 5.2. There we go. Found it right away. So we just need to add curly braces around it. So we are grouping 52 as one single thing to be in superscript. So let me find. Oh, that's the only occurrence. That's good. We publish. All right, done. Yay! Okay, so that works. Okay, I'm looking at this and go like, okay, that's correct. So in other words, when you look at the precision of what a floating point number can represent, that's the precision. Okay, if you try to add this quantity to a current number to itself, so this is a ratio. Okay, so look at this as a ratio. If you want to increment a value represented in double, this is the minimum quantity they can register when you add it to that particular number. Because you only have 52 individual bits for the mantissa. So if your quantity to increase is less than this, it's going to be lost. There's no way to specify that quantity to be added to the original number. Okay. Section 4 is something that we already know, base 10 scientific notation. I'm not scrolling up yet because you guys would think, yeah, we know about base 10 scientific notation. Do you? Because this is the syntax of base 10 scientific notation, but specified in regular expression. Okay, so regular expression is also really useful. If you right click on some explanations, it will bring you a page that will actually explain, what kind of regular expression you can use in VI. Okay, so this is VI specific regular expression, but I think variants of this they are widely used in grep as a utility program, in Perl, in PHP. Most scripting languages deal with regular expression because a lot of times when you're processing web forms and whatnot, you need to use regular expression to extract parts of some kind of string or some kind of text or perform validation. So that's why it is really helpful to understand what is regular expression, and this is specific to VI, which is an editor. Yep.
Do they also go to Nano since it's VI?
No, I don't think Nano can deal with regular expression, but you can search for that. Nano regular expression. Okay. So you can do it with a -R flag. Okay, there we go. So yes, you can also do it in regular expression in Nano, but the syntax may not be the same. So I don't know the exact syntax in Nano. So in this case, I have a full explanation of what that notation is saying. Okay, but I'm not going to read it because that's going to bore myself to death. So I'm going to just go over this, one by one. This way it's easier to explain. Square brackets are used to enclose alternative characters. So when you see the square bracket around plus minus, it means whatever is here can be a plus or a minus. Okay. \= means whatever is before this. This is a quantifier, by the way. It's a quantifier. It specifies whatever is before this can occur 0 or 1 time. In other words, whatever is before this is optional. Okay, so the sign, explicit sign of a number is optional. That's basically what this part is saying. \D is just a shorthand of the digits from 0 to 9. Okay, so whenever you see \D, it is just saying, this has to be a digit. Okay. When you see \open paren and the matching \close paren, it is a grouping. In other words, it's saying consider whatever is enclosed as a single unit. That's basically what it's saying. So what are we enclosing here? What we're enclosing is a single period. Now, because a single dot means any character, so it has to be escaped using the \. So \period means just literally a period. Okay? So this is optional. And the single period can be followed by digits, right? This asterisk means any number of the thing that is before. So together, \D asterisk means any number of digits. Can be 0. Is that okay? So when you look at this entire group, it is basically saying the mantissa of a scientific notation can optionally have point blah 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 blah. But if you just want to say, 3 is the mantissa in base 10, that's cool too. Is that okay? Okay. But then when you look at this entire group, which specifies point blah 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 blah, this entire group is followed by the quantifier of \=, which means that entire group is optional.
The only thing required so far is a number.
Yep, a single digit is required at this point. And then you also look at the same pattern here. We have open open paren, \close paren, and \=. So whatever I specify in here is also optional as well. In other words, you don't have to specify the exponent. Okay, if you don't specify the exponent, it is implied to be 0. What about the exponent itself? That E is literal. The E really literally means it has to be a lowercase e. And then we have the square bracket plus minus, which means pick one of these two. Okay, can be an explicit plus or explicit minus. But the explicit sign itself is also optional because it is followed by backslash equal to, right? And then we have backslash D, which means a single digit. But this time we have backslash plus. Backslash plus is different from the asterisk in only one little way. Asterisk means any number of. Backslash plus means at least one. So you cannot say E plus and then nothing. You have to say, every time you use E, you have to specify at least one digit after the E. Is that okay? And you can actually use this pattern to look for floating point numbers in scientific notation in the text file in BI. Nobody seems to be thinking that this is actually useful. It is very useful because otherwise, how do you specify, locate all the, scientific notations in this particular, source file? You can't easily do it, right? This allows you to do it. Now, this is not the most general form because if you think about it, this backslash D should be a plus, after that, so that you can have any number of digits to the left-hand side of the decimal point. But I'm just making it a single one.
Well, there should be a star, I think you said plus. There should be a star after it, right? Yeah.
Right. But backslash plus.
Oh, yeah, no, plus, yeah.
Yeah.
Because you need at least one.
Yeah. So this is the scientific notation, but captured in regular expression. Any questions about this? The detail is daunting because all these backslash escape sequences can be confusing, but the idea is not. Okay, the idea is simply saying I want to specify a pattern. Okay, so that we can check whether something is in this particular pattern or not. Is that okay? Do you think you will see regular expressions again? If you plan to transfer to a 4-year university and continue with a computer science program, I guarantee that you will see regular expressions again. Because you will take a class that is called computational theory or automata, okay, or finite state machines. And this is one of the most basic quote-unquote language that can be recognized by a finite state machine, which is the most basic machine that Turing has come up with. Do you think you will get to know Turing a little bit better in a 4-year university program? You betcha. Who's that guy? Some random character in a movie, right?
Oh, you have to figure out the Enigma machine.
He built the computer to crack the encryption of Enigma machines, yes. And as a result, he is kind of famous, because he is also considered the father of computer science.
And he's also the one with the AI thing, Turing test, right?
Yes, he also came up with the idea of a Turing test, which is very interesting because because Turing looks at intelligence as, can the computer fake as a human? Okay, not quite that simple, but the general idea is if you are interacting with something over a teletype terminal, if you cannot distinguish whether the other side is a real human or not, then it qualifies as AI, as intelligent. I think the actual test is actually differentiating the gender based on the communication. But the idea is the same. Okay, you have a limited interface. If you cannot distinguish whether you're talking or texting to a computer or a person, that qualifies as an AI.
I think they gave a hint of that in the movie.
Okay. I haven't watched the movie yet.
Yeah.
Yeah, I really should do that. And of course, there are people who make T-shirts making fun of the Turing test. Okay. T-shirt, I failed Turing test. I want to get myself one of these. I failed the Turing test.
When you fail it, that means you're like a robot, right?
That means I'm less human than an AI. Yes.
Yeah,
Or at least on the outside, I seem to behave less human than an AI. But most INTPs fall into this category. Did you guys do your personality test? No, sort of, kind of. Okay, yeah. Most INTPs and INTJs, should wear this T-shirt just to warn the other person. It's like you're interacting with a with a human that may not seem very human to you, but I am 100% human. All right, so that's the full description. You can read through this whole thing. So in this case, we have this example. So the sign is negative. The base 10 mantissa is 2.67. Okay, right here, 2.67. And then the exponent in base 10 is -6 because we have e minus 6 over here. The quantity it is representing is kind of this equation. Once again, so once again, I'm using the ternary operator. If the sign bit is a 1, then we use a -1 for this entire expression. If the sign is a 0, I use a 1 for this entire expression. In other words, this part is really just specifying the sign of the overall value. M10 is the mantissa in base 10, and then 10 to the power of E10 is the exponent of base 10. So together, this entire thing expresses the value that we want to represent using this scientific notation. Is that okay? So far, so good? Okay, so here's an exercise that you want to kind of think about, but it's kind of complicated, so you may not want to actually do it over the weekend, but you might want to think about it. The question is, if you know that the input to your program is expressed as a base 10 scientific notation using that particular format, how do you write your C and C++ or C++ code to recognize and break that pattern up into individual parts? That is the question. So how would you get started with this one? If I tell you that the entire thing is stored in a string already, in an array of characters, how would you approach this problem? So that's something for you to consider, to think about it, because we are going to work on the homework assignment, and that's exactly what your program needs to do, is to read a base 10 scientific notation and convert it into the internal representation of a double. So the very first step is to break up the string and get those components out. The sign, the base 10 mantissa, and the base 10 exponent. Okay. In your 360 class, did you guys learn how to do parsing? From a string or from cin or from some kind of sequential source.
Turn it into binary turn it into binary or ASCII?
No, just any type of parsing. Like you look at one single character in an array of characters, and then you decide, okay, I need to go here, I need to go here, or this comma is separating this from the next thing. So you have to recognize what the string is representing by scanning the string sequentially. Did you guys learn techniques like that? Yes? Somewhat. Okay. So that might be something that you want to think about, okay, on top of the other, informal, assignments that I given you earlier. Yep. Mm-hmm.
That homework will be in C or C++, or?
You can do it in either one. I personally just do everything in regular C, because C++ I don't think it's going to give you a lot of extra help in this case, because you'll be pretty much using your own code to scan through the entire array. So the only thing C++ is kind of superior is you can pass things by reference. Whereas in C, you have to pass a pointer and change what the pointer is pointing to. It's a little bit more messy and a little bit more dangerous, but other than that, C++ doesn't give you a whole lot of advantages. Okay. Any questions about double precision floating point format up to this point? Questions? Good, I didn't run out of material. Because I didn't type a whole lot more than this. So conversion from base 10 to base 10 scientific notation to double is something that we are going to do. It will be messy. Because you're giving a number. So this is a preview of what we'll be talking about next week. you are given a number represented like this because you have a base 10 mantissa and a base 10 exponent. But you want to convert it so that it would use a base 2 mantissa and a base 2 exponent. Okay? That is going to be messy. Because some people may say, oh, we can just use a whole bunch of log and exponent functions. No, that's not what you want to do, okay? Because that's going to take like a long time to do it. So the only thing we want to do would be by integer arithmetics, okay? Integer division, integer multiplication, integer addition, integer subtraction, and that sort of thing. We don't want to use floats or doubles because that would be like a chicken and egg problem, right? We're trying to deal with doubles and you have to use double operations. That doesn't work very well. Yep.
Is that why mathematicians in the past were turning them into fractions as close as possible to the number and then working from there?
I suppose so. I mean, that's one way to do it. Yeah, but this is what we'll be talking about next week. So, when you have time over the weekend before Tuesday next week, just kind of think about these things that we have talked about today. Yep.
Well, let me ask, when are we going to get that homework? The converting thing?
It'll be after the subtraction thing is due. So the subtraction is homework assignment is due on Tuesday. So I'll assign it on Tuesday, but you will have 1 week to work on it before it's due. Yep.
Is it also going to be the homework in Logitech?
This is not in Logitech, unless you want to. Yeah, this is not going to be in Logitech or Logitech. This is going to be a regular C++ program. You can probably do it in Logitech, but it's going to be pretty hard. Yeah. Okay, I'm going to take that on as a challenge.
You gonna try and do it in Logitech?
Yeah, I'll try to at least figure out how to, because Logitech has divisions. There are division operators and stuff like that. So the only thing I need to do is to have a mechanism to pump the numbers over and over again through a filter, and then every time it goes through the filter, I'm gonna have to kind of generate some kind of output and somehow be able to capture the output. Pretty sure it's doable. It's just how much material do I need to get it to work. All right. Well, I'm going to conclude the lecture here. There are no structured instruction in the lab portion, so it will just be you working on your subtractor homework assignment and ask any questions related not only to the subtractor, but also topics for today or any other topics related to this class.